nella classe arancione dentro tranquillo.
Hello, good evening, all. Welcome to the class. Uh, we'll wait a couple of minutes so that if somebody else wants to join, they can join. And meanwhile, I'll also set up my tablet. Okay. So, just to check, am I audible?
Yes,
Yes, okay.
the voice is little low.
My voice is low.
Yeah, the volume is low, slightly low as compared to other classes.
Okay. Let me check it. Is it better now? No? Oh, give me a second. Okay. So, actually, today I'm in my lab. Maybe that's why it's slightly low. But I hope it's not too low.
We can start.
Okay. So, before starting with the problems, uh, are there any doubts that you want to discuss?
Yes, sir. There is one question that I wanted to ask you about.
Yes, yes, you can ask.
For that, is, can I can I share my screen to show you the question?
Yes, yes, you can. Wait a second. Hmm, yeah.
Mhm. The C part of this question, what are the classical and quantum mechanical probabilities of finding the electron at r greater than 2a? So I I found out the quantum mechanical probability, but the classical part, I was not satisfied with the answer that my teacher gave me.
Okay.
I'll also just go through the question answer. I will also share you the PDF that was given by my teacher.
Okay, wait. Let us first read the question carefully.
Okay, sir.
So we are given a wave function for an hydrogen atom, and we know that it is separable in theta, phi, and r. The radial part is given as this. Okay, so we are only focusing on the radial part, and also L is equal to 0, meaning the ground state. Good. So first of all, we have to show that this is a solution of the equation. Yeah, that is, I think we can just substitute for psi in the equation given above, and that should be enough. Then we have to find the values of capital A, small a, and the ground state energy, n is equals to 1. Okay. Then we calculate the mean distance, square mean distance, and the most probable distance between the electrons and the nucleus in terms of Bohr radius. Okay. What are the classical and quantum mechanical probabilities? Yeah, okay. So, yeah, we have read the question. Now, what is your doubt?
Now I am opening the solution. So quantum mechanical probability, it was given using this result.
Yeah, from 2a to infinity. Yes. Yeah. So this is
Fine.
basically psi squared. Yeah. Yeah. Correct.
So this part we were able to calculate. But
Yes.
classical probability equal to 0 is what has been told
Okay.
here.
Yeah. So you think that it should be some non-zero value, is it?
I don't know why he took it to be 0.
Okay. So your doubt is that the classical probability in the answer is 0, but you don't understand why it is given to be 0. Correct?
Yes.
Okay. So uh, hmm. What? Okay. Let me ask you. What do you think is a classical model of the atom? Right. So quantum mechanically, we know that we have this wave function of an electron, and this wave function is an exponential, this e to the minus r by a type of wave function. And to find the probability, we can just square it, and that will give us the probability. Okay. But if you think classically, right, classically, where we do not have any kind of wave function associated with the electron, right, it is just like a particle. So then classically, what do you understand will be the classical model of an hydrogen atom?
Classical model of hydrogen atom. Why?
Classically, yeah.
I think there are only certain distances 0.529 into n square by z Armstrong, where
Yeah,
we find the electron.
correct. So, okay, to understand this, let me give you an analogy. So, quantum mechanically, let's consider another system. Okay, let's say we have a potential well. Okay.
Madam, we can't see your screen because this screen is being shared.
Sorry.
We cannot see your screen. Whatever you are
Sorry.
seeing, that is not
Okay, okay.
visible.
Sorry, I'll share my screen. Visible now?
Yes.
Okay. So what I was saying, let us consider a potential well, right? Let's say this is some potential V naught, right? Let us say this is our zero level, so energy is zero, and then we have V naught, which means that it is some kind of an attractive potential, right? And let's say we have a particle here with some energy E. Okay. Now let me call this as my x is equals to 0, and this is, let's say, my x is equals to a. Okay. And so the problem is that we have a potential well, x is equals to 0 and x is equals to a. The depth of the potential well is v naught and energy of our particle is E. Now classically, okay, classically outside this region, so for x less than 0 or x greater than a, for this region which is outside, okay, for this region, what will be the probability of finding the particle? Yes, Harshul, what do you think will be the probability classically?
Uh, Classical.
Yes, classically meaning, okay, classically meaning that this potential well has this size of v naught, okay, and our particle only has this energy E, okay, so this energy is only this much.
Then it won't be found outside that well.
Correct. So then P will be 0, and this is only classically true. Quantum mechanically, you can have some finite probability, right? Outside. Yeah.
Yes, sir.
So now this is very similar to the hydrogen atom. Okay. So instead of X, we can write R. So this is where we have our nucleus, and then this side is not important. Okay. We have our nucleus here, and this is R is equals to A. R is equals to A. Okay. Only difference is the potential well is not a perfect square well potential, right? It is not a perfect square well potential there, right? It is more like a Coulomb kind of a function, right? So it's not a just it's not a perfect square, but more like a Coulombic potential. So if the particle has less energy and it is inside this thing, so it will remain inside, and if it has more energy such that it is outside, so it will remain outside. Okay. So there is no uncertainty. Okay. Classically, there is no uncertainty in position, right? So it is well defined. If it is if it is a bound particle, right? If it is a bound particle, so if I draw my nucleus and I draw my electron here, okay? Let's say this blue one is my electron. Now this electron is bound to this nucleus by Coulomb potential. Okay. Classically, it is not possible that this electron goes away to, let's say, this position, right? Okay. So the probability of finding electron at distance, if let's say this is A, at distance greater than this A will be 0, because it is like a bound system. And classically it will always remain bound. And there are no uncertainties in the position. We have found a position that the particle is at this position, and then we don't give any perturbations, or we don't give any new potentials or anything, so the particle will just remain there. Okay.
Right, sir.
Right.
But in
Yeah.
the question, it's not mentioned that A is the radius of the.
Yes.
Uh,
So in, if you look at problem, so the first part of the problem, if I remember correctly, I think it's the first part. There you have to find capital A, small a, all these things, right?
yes,
Yes. So what you will find out, that this small a is actually the, and then in the second part you have to find the average position, mean position, all these things. So what you will find out exact is that this small a is the Bohr's radius, or it is the it is the most probable this thing, the distance of this electron in the ground state. So it is not given in the problem, you are correct, what this a is, but in the in first two parts you have to find out what this a is, and then what you will see, that this a is nothing but the Bohr's radius, which is the radius of the first orbital. Okay.
right, sir.
Right. Okay. So should we move on?
Yes,
Okay, then let us solve some problems, and if we have any more doubts, then we will discuss them in the last part of the session. Okay. So let's look at the first problem. Here we have this YLM function. Okay, we have already encountered this. So this is called spherical harmonics, right? The solution of this D. Yeah. So there is nothing much to solve here, right? So the answer is this. Okay. I'll just say that uh, the L square. Okay, this L square operator, it commutes with all of them. It commutes with Lx, it commutes with Ly. Sorry, L square Ly, and it also commutes with Lz. And this is 0. And this is by convention. This is by convention that we give special preference to Lz. Okay, and then we just and then we write these things. So if this is Lm, so L square will give us these eigenvalues, right? And Lz will give us this eigenvalue. Okay, so pretty standard. Okay, so this we already know. Another true or false problem. Now here we are given that we have a spinless particle Okay, a spinless particle moving in a potential V of r. So the potential that is given to us, V of r, is radial potential, right? It has this radial symmetry. For example, the Coulomb potential, right? And then the question is the time reversal operator T commutes with the Hamiltonian. Okay, so what do we know about this time reversal operator? So, do you know about this time reversal operator?
No, sir.
Okay, then let me tell you. So, time reversal operator, it is denoted by T, okay, is a complex conjugation operator. So if we operate T on a wave function psi, we get psi star. Okay, so operating T on a wave function psi gives us a psi star. Now we have to find the commutation of T, right? Commutation of, so if T commutes with the Hamiltonian. Now what is our Hamiltonian? Our Hamiltonian consists of two parts, p square over 2m and then a radial potential. So we are given that the potential is radial. Okay, so let's consider the momentum part first. So we have p, okay, now we cannot write this as d by dx because now we are in 3 dimensions, so we will write this del operator. Okay, okay, so now this you can see it is purely imaginary, purely imaginary. So basically if we do this thing, TP T inverse, this will just give us minus P. Why? TP T inverse will give us minus P because this is purely imaginary. So we'll have iota, iota star will become minus iota, and then again we have another T here, so we'll have an minus iota multiplied here, which will give us just minus 1. Okay, so this implies, because here we have p square, so then this T p squared T inverse will give us minus p squared, which is p squared. Okay, so this implies that the kinetic energy term is invariant. Moreover, the potential energy term this is purely real. Okay, this is purely real. Therefore, this T V of r T inverse will again give us V of r, which implies the potential energy term is also invariant. Therefore, the entire Hamiltonian remains same, which means h comma t is 0. Okay. Any doubts in this one?
Can you explain t minus 1 is equal to minus b?
Yeah.
So it little bit elaborate.
Okay. So before that, did you understand what we are doing? Why we are doing this TPT inverse? Hmm?
Is this the expectation value of p? We calculating by this t minus 1?
Mm-hmm.
Will it keep the expectation value or
No.
it's
No.
taking something else? Okay.
This will not give us the expectation value. So what this is doing? Okay. So because this. Okay. So what this? Okay. So this T, which is the time reversal operator, it is like a complex conjugation operator. Okay. So what it does is when it is operated on a wave function, so it's takes it from psi to psi star. Okay, it's so essentially it's like taking the complex conjugate of a wave function. Now notice that this operator is not giving us any eigenvalue. Okay, so this is not an kind of eigenvalue equation, right? So then what we are doing here, we are doing a transformation. Okay, so to determine if T commutes with the Hamiltonian, so we are looking at how it transforms the position and momentum operators. Okay, so let us do this thing again. So this TPT inverse one, no, let me write it again. So here we have T and then P and then T inverse. So if I write this explicitly, it will become minus iota h cut delta and then T inverse. So when this mm, so when this T basically will operate on this, one second. So when this T operates here, essentially what it will do, it will just give us the complex conjugate of this quantity, right? Therefore it will give us iota h cut delta. Okay, and this is nothing but minus p. Okay, so this, okay, what this means now, this time reversal symmetry, it comes when we study magnetism, if you are familiar maybe. If not, it's not a problem. So physically what it means, so physically it means that reversing the time, because this is a time reversal operator, so reversing the time, okay, reverses the direction of velocity or momentum, right? Or momentum. Okay. So now imagine that your particle is traveling in the, so you see that your particle is here and it is traveling in this direction. After some time it is here, traveling here, traveling here. Now if you kind of rewind this picture, rewind this video of the particle traveling, what you will see upon time reversal, so upon time reversal, you will see that our particle is traveling this way. Correct? So we have flipped the direction of momentum, right? Is that correct?
Yes.
Yes. Okay. So that's why when we see how our momentum transforms upon time reversal, we see that it gains a minus sign. Now if we apply the same logic to our position coordinate, okay, so if we look at the position, let's say this is x equals to 1, 2, 3, so on. So upon time reversal, what happens to x? So this x remains 1 only, this remains 2 only, and this remains 3 only. Only thing is the velocity is changing. But upon time reversal, this does not mean that our x goes to minus 1. This is wrong, right? And x does not go to minus 2. This is also wrong. So our position x or r upon time reversal stays r, but our velocity or momentum upon time reversal becomes minus p. Is that clear now?
Yeah.
Yeah? Okay.
Sir, but what we are doing is, see, you told time reversal operator times psi equal to psi star, and we are doing that for TP equal to minus P.
Yeah.
But what's T inverse term doing over there?
Okay, so what we are doing is we are looking. So this is, hmm. So this thing, right? So when you have this T on both sides of your P, so first of all, okay, one thing that I should also mention that this T is a this thing unitary operator. Yeah. So T is a unitary operator. So whenever, so essentially, unit when we do this thing, U inverse, where A is any operator and U is a unitary operator. So what it does, it tells us how this operator A will transform under this unity transformation. Okay, this will not. Okay, so here, for example, this will not change the magnitude of P because it is a unitary operator. So operating it 2 times will give us 1. Okay, so it will not change the magnitude. Okay, so if our momentum was, let's say, 100, doing this operation T P T inverse will still give us 100. Only thing is it can give an additional minus sign or an iota depending on what this operator U is. So it is like a transformation in the phase space. Okay, and here we see that this transformation in the phase space has completely flipped our momentum operator P. So in general, okay, let me tell you quickly. Let's say this is our phase space. Let's say this was our P in some random direction theta. So this transformation TPT inverse, it can basically rotate your operator P in this phase space, meaning it can give you some additional phase phi. Here we see that it has given an additional phase of pi, right? 180 degrees, which has made this P to be minus P. Okay. So this, when we have a unitary operator, doing this set of operations tells us how our momentum transforms upon this, upon applying the time reversal operator. Okay. So we are directly looking at the operator instead of a wave function. Then what we find is that the momentum operator P under time reversal gains a minus sign. Physically, this means that if you reverse the time, you will think that a particle is moving in the opposite direction, right? So it has a negative momentum, right? The opposite momentum. Okay. But since r is real, we will not, so we will not have this because there is no iota. Okay, let me erase all these things. Okay, so since r is real, if we do this t v t inverse, so we get t v of r, t inverse. Now operating t here, because it is a purely real number, so its conjugate remains the same, right? So it is just v of r, right? So we don't have any minus sign or anything. But notice that in the Hamiltonian, we have a p square term, right? We have a p square term. So this, we have to apply this operation on p square. So it will give minus p times minus v, so p square. So the kinetic energy again we find is invariant, which should also be physically true, right? If we reverse our video, we will not say that this particle has suddenly gained a negative kinetic energy. So ultimately, our Hamiltonian remains as it is under time reversal symmetry. Okay.
Fine.
Sorry.
Sir, what bothered me was, so
Mm-hmm.
I understood your explanation initially about why T of V T inverse equal T of V equal to V because that's purely real. But
Yeah.
we are multiplying an additional T inverse term. That's where I am getting stuck again and again. Uh,
Uh, okay. So let's say, okay, another way to, it's just it's just way of writing things. So what we need to prove? We need to, I can write it like this. We need to prove that this thing is 0, right? Right?
yes,
Basically, this is what we need to find. Now, what is this thing? This is nothing but ht minus th. And because this is equals to 0, I can write it like this. Correct?
yes,
Okay. Now, if I multiply both sides by t inverse, what I'll get? Is this correct?
yes, sir, yes,
So, proving this is essentially the same as proving this, right?
true, true.
If this statement is true, that will automatically mean that this statement is true. Okay? So
Yes,
then I want to see if this statement is true. So instead of h, what I am doing is I am doing this thing. So first I am doing p squared by 2m, and then I am doing this thing. Okay? And we see that both of these, so this is giving me p squared by 2m, and this is giving me v of r. Adding, we again get the Hamiltonian. So we prove that this RHS and LHS are same. Now does this make little more sense? Why we are doing this
mm,
T inverse?
yes, yes, sir, yes.
Okay. Okay, then let's move on to the next problem. Okay. What do we have here? We have an operator P of r associated with the radial component of the momentum PR, and an operator capital R associated with the radial component small r, and their actions are defined below. Okay, so it is given to us that this P of R, when we operate it on psi, it gives us this thing like a momentum operator, and R, capital R operated on psi gives us this thing like a position operator. Then we have to find the commutator P of R and R. Okay, so we are given uh, what 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 we will get when we operate. So let's find out this quantity P of R and capital R. Let's operate it on a wave function psi. Okay, so this will give us P and then R psi minus R P psi. Yes, and now using the two equations that are given in the problem, we can write these R of psi and PR of psi as follows. So this then becomes minus iota h cut 1 by R del by del R, and instead of psi R, so this R operating on psi will give us an additional R and psi. Okay, and this second term, so this will give us just R multiplied by minus iota h cut 1 over R and del by del R, and then R psi. Okay, so let's first solve for the first term. So what we will have here, we will have minus iota h cut by R, and then this is R squared psi, right? So del by del R squared psi. So this will become, so once we have to take derivative of R squared, so that will give us 2R psi, and then we will have R squared del psi by del R. Okay, and now for the second term, so this R and R, they'll cancel out, and then we'll have this minus iota, so this will become plus iota h cut, this will become plus iota h cut, and then del by del R of R psi, right? Del by del R psi. So this plus iota h cut, and then again we will have two parts, so derivative of R will just give us 1, so this will be psi, and then plus plus, and this will be R times del psi over del R. Yeah. Okay, so then we can rewrite this entire thing. Okay, also this R will cancel out here, and it will cancel one of the R's here. Okay, so then we can rewrite. So let's take out this minus iota h cut outside, and inside what we have, we have 2 psi plus del psi over del R, sorry, I missed one, R plus R times del psi over del R, and because we have taken this minus attached cut outside, so here we will have minus psi and minus R del psi over del R. Okay, so these two terms, they'll just cancel out, and this 2 psi minus psi is just psi. So we have minus iota h cut psi. Okay, so writing this thing again. So we have this commutator of P and R. This gives us minus iota h cut psi, which implies that this commutator P of R is nothing but minus iota h cut. Okay, so option A. Option A. Any doubts?
See, in this question, can we say that PR and capital R, they both have same eigensets, psi
Sorry?
R and psi R. The eigensets of capital PR and capital R operator
Eigengets, yes.
are the same.
Hmm.
And their commutator also has the same eigenset, psi R.
Yes.
So, can we infer something from here? See, if the two operators have same eigenset, I forgot what other properties do they share. Do they commute? I mean, I thought that they might be commuting if they have same eigensets. But I mean, can you just
Mm,
elaborate this? If they have
uh,
same eigenset and their commutator also has the same eigenset.
okay, so one thing that I would like to mention explicitly. So, do you think that this is an eigenvalue equation?
Yeah, I think because psi r and psi r is the same on both the sides, and
Mm-hmm.
when it is being operated by capital P,
Mm-hmm.
we get minus iota h bar 1 by r del by del. Okay, no, I'm not sure. Because these are,
So,
those are
so
the,
if we compare this with our standard eigenvalue equation, then our lambda here is minus iota h cut 1 by r and del by del r.
into r.
R.
Yes, these are the constant.
Yes. So this is not an eigenvalue, right?
Okay.
This is not
Neither
an
the
eigen.
other one. Neither the
Neither
right
the
and the
other
other
one.
one.
Neither
Because
the other
r is
one.
also again a
Exactly.
delta. Okay.
Exactly. These are not
Okay.
eigenvalues.
Yeah.
Yes. So these are not the eigenkets. These are just some wave functions, and this is what the operation P and R does to those wave
Mm.
functions.
Okay.
These are
Okay.
not eigenvalue equations. Okay, and that is
Their
so if
commutator
they
is,
yes
but their
you
commutator is a eigenvalue equation.
their commutator. So this equation, right? Yes,
Yeah.
this is an
Yes.
eigenvalue equation.
Okay.
However, this does not correspond to a. So you can see the eigenvalue is not real, right? So this will not correspond to any observable as such,
Okay. Right. Right.
right?
Right.
Yeah.
Ah, right.
So this will not be like some form of energy or momentum or something, right?
Mm-hmm.
No,
Mm.
we cannot associate it with some physical quantity.
Yeah. That means this commutator is not a Hermitian operator.
Exactly, it is not a Hermitian operator. And if okay, one more comment. If these were the eigenkets, right, of P and R, then we would have got the commutator to be 0, right?
Zero.
Because we
Yeah.
are
Yes.
measuring both of them at the same time. We can measure both of them at the same time, yeah. So we would have got 0. But here, because we don't get 0 of the commutator, that also implies that they do not share same eigenkets. They have
Mm.
different eigenkets. Okay. Should we move on?
Yes.
Okay. Let's go to the next problem. Yeah, okay. So we are given that this is a ground state wave function of hydrogen like atom. So we are given this wave function psi 100. Okay, it has this radial form. Okay, and 100 means ground state.
Mm.
Now we are asked that if the inter-electronic repulsion means that in helium, so helium will have how many electrons?
Mm, one electron. If it is,
No.
sorry,
Helium,
can you repeat?
it is not He plus, it is just He.
The two electrons.
2 electrons, right? So helium has 2 electrons. Okay, let's say this is 1 electron, and let's say this is our second electron. So what the question asks, that the inter-electronic repulsion is ignored. So basically they do not feel each other. They do not see each other. They do not interact with each other. Okay.
Mm.
And then what we have to find? We have to find the ground state wave function of this helium atom. So that is our problem. Do you want to guess or should we solve it? Okay. If you want to take a guess, which option would you select?
D, is it D or D?
B. Okay. Harshul, do you want to take a guess?
I don't know anything to take this. Sorry.
Okay. So it will not be B. Okay, let me tell you why. Okay, let's solve this. Okay, so one thing that you can easily see, that this exponential part, it has this z r1 plus r2 terms, right? So this z
Mm-hmm.
r1 plus r2, all of them. Okay, which means that we can, so this is exponential, right? Exponential minus z r1 plus r2, which means that we can write this as a product of two exponentials, right? So e to the power minus z r1 and e to the power minus z r2. Correct? And we know that from the given wave function of hydrogen like atom, that for an electron we should have an a naught here and an a naught here. Okay, and then we should also have this prefactor multiplied by both of these things. So which will, let me raise this, which will just give us a square of this thing. So 1 over pi and then z by a naught q and multiplied by this thing. So this again we can write as just one exponential minus z r1 plus r2 by a naught. Okay, which means option A.
Okay.
Okay, so this is a little shortcut where we are using already that this information is given in the options, that the exponential function has this form. Okay, but we can also do it properly. So one very important information that is given to us, that these electrons do not interact with each other. So then our total Hamiltonian H will be just sum of the individual Hamiltonians of the two electrons. There will not be any additional interaction terms, right? Because this is just 0. We do not have any interaction. It's just energy of one particle plus energy of the second particle. That's it. Okay. And when we have a total Hamiltonian of this form, then our total wave function, so our total wave function psi is just product of, so psi 100 ground state r1 and psi 100 ground state r2. So then our total wave function is just a product of two wave functions. Okay, and then this is very trivial now. So this factor will just get squared, right? So it will give us 1 over pi z over a naught cube, and then here we have exponential minus zr by a naught. So this multiplied by exponential minus z r1 by a naught, sorry, multiply it and then multiply this with minus z r2 by a naught, and then straightforward 1 over pi z by a naught cube, and we can write it as a single exponential function. This will be r1 plus r2 entire thing divided by a naught. So this is our side. Okay. So when we do not have any interaction and we can treat the particles separately like this, right? Then the total energy is just the sum of individual energies, and total wave function is just the product of individual wave functions. That's it. Okay. Any doubts?
How far this approximation is from the actual situation?
Sorry.
This approximation that they are not interacting,
Mm-hmm.
far it is different from the actual situation. And in reality, these both the electrons, they have opposite spin.
They also have
So,
spins, yes.
so they are actually not, I think they are not repelling each other so much because they are in the same and is equal to one state. So actually they are already very close to each other.
Huh. They are already very close to each other. That is correct. They are in the same
So
state. So that's why we
they
are able to
are
write
not
100
repelling each other.
100.
Actually, they are not
Yes.
repelling each other so much.
Yes. So this you can take this approximation and you will get some reasonable numbers. It will not be very off. You
Yeah.
are correct. Yes. So okay. So in atomic and molecular physics, we generally study spectra, right? So emission spectra, absorption spectra,
Mhm.
and then uh, basically what we start to see that as we keep on improving our experimental setups more and more, that we start getting finer and finer structures, right? So
Mm.
then to explain those we have to consider more and more interactions. So you'll study about fine structure and then
Mm.
hyper fine structure, and then we
And
have
that
to,
only in the presence of magnetic field.
yes, magnetic fields. Then we also have to consider the electron-electron interactions. We also
Yes.
have to consider the basically,
SS coupling, intercoupling.
yes, couplings, the orbital couplings, and finally we consider the nuclear spins,
Yeah, nucleus coupling.
nuclear spins,
Yes.
and then we go to the hyperfine structures. So this is a very like first level approximation, right? So we do not consider any interaction, and then step by step we can keep on adding the interaction to explain our experiments. Okay, but this is a you can say very crude approximation. The energies that we will get will be reasonable, but then again we will not be able to explain the structures that we see in the experiments.
Uh, Manu, can you connect me from the other device? I'm changing the device.
Yeah, I'll admit. Okay. Okay, so let's take a small water break and then we will resume with this problem. Yes. Okay. So let us begin. Okay, now what are we given? Okay, we are given a coherent state. Okay, so from our previous class, if we remember that a coherent state, okay, they have also mentioned that this is an eigenstate of the annihilation operator such that A of alpha gives us alpha times alpha. Okay, so we are given a coherent state alpha, this is what we are given, and then they say that the probability p of n of finding the state alpha in the number state n is equals to 2 is exponential this thing. Okay, so probability p n is equals to 2 of finding alpha in the number state n when n is equals to 2 is, now this probability that it is given as to be exponential, there is a small typo here, so it will be minus mod alpha squared and then alpha to the power 2q by q. Okay, and then what do we have to do? We have to basically find q. Good. Now in terms of the number operator, sorry, in terms of this number state n, okay, this was discussed in the previous lectures that we can write alpha in terms of n as a summation, right? N is equals to 0 to infinity alpha to the power n divided by under root n factorial and the nth state. Yeah. Okay, so this is what we have now. Then so the probability of finding the state in a specific number state n, okay, pn, p of n, basically it will be n times alpha and mod squared, correct? So if we multiply this alpha, sorry, if we do this operation, so what we get, we will get n alpha, we will get n alpha as e to the minus mod alpha square by 2, and then here we have sigma. Okay, I think I should write this as, let's write it as, instead of n, let's write it as k. Okay, because it's just any number, right, which goes from 0 to infinity, any integer. So here we will have k going from 0 to infinity alpha k over under root k factorial and then n times k. Okay, now this k, okay, now tell me what will happen to this nk. So what is the value of this nk?
That would be Kronecker delta.
Yes,
Come.
so this is 0 when they are not equal and this is 1 when they are equal, so we'll write this as delta nk. Okay, which means out of all these terms, that k is 1, 2, 3, 4 and so on, the only term when k equals to n, survives, right? All other term they go to 0. Therefore, our n alpha becomes e to the, sorry, it becomes e to the minus mod alpha square over 2, and out of all of this we have only the nth term, so alpha n and then this thing and then this thing. That's it. Okay, and now to find p of n we have to do a mod square of this thing. So our p of n will be, so squaring this will just, so this 2 will go away. Okay, so this 2 will go away and we will have e to the minus mod alpha square here, right? And then this will be alpha to the 2n. Okay, should be mod alpha to the 2n divided by n factorial. Okay, and now let's compare this with what we are given. So this thing we are given exponential minus mod alpha square alpha to the 2q divided by q. So we are given that the probability is e to the minus mod alpha square alpha alpha to the power 2q divided by q, right? Q, and this is what they get for n is equals to 2. Okay, so this is what they get for n is equals to 2. So if we put n is equals to 2 here, so n is equals to 2 here, that will give us probability as e to the minus mod alpha square multiplied by mod alpha to the power 4, and 2 factorial is just 2. Now if we compare both of them, this equation and this equation, what do we find q to be? We find that q is 2.
Sir, in the question they asked Q value. It's Q
Yes.
value alpha power 2q by q. So over there n factorial must be equal to n for that equation to be true.
No, so they say that, okay, let's read the question again. They say that the probability p of n of finding the state alpha in the number state n is equals to 2 is this number, something they are saying. We are getting this thing.
Okay.
Okay, so
Okay.
in the final step, after we have computed p of n, we have to put n is equals to 2 and then we compare. Okay,
Okay.
now if you compare these two which I have put in a box, they are exactly matching for q is equals to 2. This is because 2 factorial is same as 2, right? That is what you want to ask, right?
Yes.
So for any other state, this wouldn't have matched. It's only matching for the 2 factorial. Then they would have to put another factorial here, right? Another factorial here to get it matched. Okay? But because it is 2, we do not need that factorial, right? It is already matching.
Yes.
Okay? Okay. So let's move on to the next one then. Yeah, okay.
What is the importance of coherent state in that problem?
There is no importance as such.
Mm-hmm.
The problem is more about, so that this coherent state, okay, it's like a, as they have also, okay, as we have written here, this coherent state you can think of it like some combination of your numbered states, right? 1, 2, 3, and so on, right? So,
Okay.
for example, this when we write states like this, what do you understand by this? So when this is 0, we say that that is our ground state,
Mm-hmm.
and 1 first excited state, and so on. So this coherent state we can write as a sum of multiple such states, right? Some coefficient c1 time, sorry, c0 times the 0 state plus c1 times the first state, and so on. Okay. So when we when we can write this state like this, then we can obviously we can ask a question that what will be the probability of finding this coherent state alpha in any number state, for example, ground state.
Can we say that in a harmonic oscillator, all the states are coherent states?
No,
Is it
but
making any sense?
mm, it is okay. So it will be a better statement to make that a, a linear combination of these with some added factors will give us a coherent state.
Okay.
Not not all the individual states are coherent states.
Okay. So
So
coherent state has to be a superposition of few states,
yes, yes, exactly, exactly.
and in which all the numbers are maybe in the same phase. Coherence generally, when we relate it with an interference, we say they are in same phase.
Mm-hmm.
So does that thing also apply here? That
Do
they are
you?
in superposition, but they are in same phase.
Yeah.
Or what?
So do you remember where this coherent states concept came from? We discussed this briefly in the last class.
Yeah, I think I asked in the last class also.
Yeah.
I don't.
So there. Okay. So there we basically there we tried to show that if you take these numbered states, right, these n states, to say, if you take these n states, and then we try to find the basically this quantity xt and pt. So we expect that these quantity they should have an oscillatory uh, time factors, right? Some sine omega t, cos omega t
Hmm.
kind of a function, because this is an harmonic oscillator,
Okay.
right? But if you consider these states, the 0 state, 1 state, then what we found out that we do not get any sine omega t or cos omega t kind of a
Mm-hmm.
function.
Mm-hmm.
So then it is very difficult to make sense of these states when we compare this with our classical counterparts, where we see a clear oscillatory function, right?
Mm-hmm.
If instead you use this coherent state, if instead you use this coherent state alpha, then we showed in the last class that indeed we get a oscillatory kind of a
Mm. Okay.
sine omega t, cos omega t thing.
Yeah. Okay. Fine.
Okay. Yes. So then this question is about finding the probability of this coherent state in, let's say, when it collapses to any one of this its constituent states.
Okay.
Now,
Okay.
one comment that I can, okay, so let me bring this one down here. So this is what we find, right? Let me copy this and paste it here. Yeah, so this is what we find, correct?
Hmm.
Can you comment on this probability function? Like, does it look familiar to you? Have you seen this kind of a function before?
This is an exponential some.
Poisson distribution.
Sorry, exponential
Po- Poisson distribution function.
Poisson distribution function. Yeah, so it's like a your very typical bell curve that we see, right? This kind of a function.
Okay.
So, for example, okay, this is this is a Gaussian, right? This is a simple Gaussian wave function. So it means, okay, so it means that the maximum probability is at the center, and then this probability decays as exponential squared. Okay, not just e to the x, but as exponential squared, right? So it decays very rapidly. So as your alpha is increasing, then this decrease is even larger. Okay, uh,
And
one
the mean value is, where is the center value? It decays on both sides of the center mean value, right?
yeah,
Mean
it,
value is what?
so for mean value, if we put, I think here it is coming out to be uh, I don't know.
I think mean value is lambda for the Poisson distribution, so that would be
Yeah,
mod alpha squared.
yes, that will be mod alpha squared. Correct. Yes. Okay, anyway, so the point is this kind of a distribution is very common in nature. So for example, our classical particles, so an ideal gas equation that we write, they also follow this kind of a distribution. And you can find many more physical phenomena that will give you this distribution. So if you flip a coin multiple times, so that will also give you similar distribution. Okay.
Right, right.
So then what we can comment on is, so this is more like a classical distribution. It is also called a classical distribution. When we consider our consider our ideal gas particles to be classical, then we get this kind of a distribution. So the probability distribution of these coherent states is giving some kind of a classical distribution, which is also kind of expected because they also give us a classical analog in terms of sine omega t and cos omega t variation of the xt and pt values. Okay, so let's move on now. Okay, so what do we have here? Okay, so we still have some time left. Good. So now this is a problem on the properties of Pauli matrices, and then we have to find out the value of this expression. So we have two exponential functions, exponential minus iota pi sigma y by 2, sigma z, and then exponential iota pi sigma y by 2. Now, okay, so the question says using the properties of the Pauli matrices. So the first property that we are going to use is this identity. Okay, that e to the iota theta any sigma, this can be sigma x, sigma y, sigma z, doesn't matter. So this gives us cos theta times the identity plus iota, and then again this same sigma x, sigma y, sigma z times sine theta. Okay, so the first term, this first term will then become, so here you see on comparing, theta is minus pi by 2 here, right? So theta is minus pi by 2. So cos of minus pi by 2 is same as cos of pi by 2. Let me write. So this first term will give us cos of pi by 2 times I, and this plus will become minus, then we will have iota, and this, because here this is sigma y, so this will be sigma y and sine of pi by 2. Okay, so cos pi by 2 is 0, so this term just goes to 0. Okay, and this sin pi by 2 is 1, so this gives us minus iota sigma y. Okay, so this is the first term. Similarly, the third term or the third factor will again give us cos pi by 2 I, and this time plus iota sigma y sin pi by 2. So again this term is 0 and this gives us iota times sigma y. Now multiplying all three terms, d, yeah, yes. So multiplying all three terms, so we have minus iota sigma y, sigma z, and then multiplied by iota sigma y. So this iota square is minus 1, minus minus gives us plus, so this is just sigma y, sigma z, and again sigma y. Now this sigma y, sigma z, now we'll use the second property of these Pauli matrices, which is that sigma y, sigma z is nothing but iota times sigma x. Okay, so this thing then becomes iota sigma x sigma y, and again sigma x sigma y just gives us iota times sigma z. So this then becomes iota squared sigma z or minus sigma z. Okay, so this entire thing becomes minus sigma z. Therefore, option D. Okay, now do you know how to basically, have you seen this identity before for the Pauli spin matrices? If not, then if time permits, we can solve this in the end. Okay, if you have seen this and you know this, then we can skip that part. Okay, so do you want me to prove this in the later part today?
No, I think maybe we can move forward.
Okay. Okay, so let's do next problem. Now, okay, again this should be an easy problem. We have to find the value of this expression in the standard angular momentum basis. So we have so this is the eigenstate Lm, and we have to find out the basically the expectation value of Lx squared, right? So Lx squared, this is what we want, to find. Now this Lm, so this wave functions Lm, these are generally eigengates. So these are eigengates of L squared and Lz, right? So we have to convert this Lx square to Lz and L square. Okay. Okay, so how we can do that is, we know that total L square is nothing but Lx square plus Ly square plus Lz square. Okay, and by symmetry Lx square and Ly square are equal. So this implies L square is equals to 2 times Lx squared plus Lz squared, or Lx squared is nothing but half L squared minus Lz squared. Hmm. So this is our Lx square. Now if we go back to our first line here, this then becomes, so our expectation value becomes Lm, let me take out this half outside, and then L squared minus Lz squared and Lm. Okay, so this is then half L squared operating on Lm. What will that give us? That will give us L times L plus 1 h cut squared, and Lz squared operating on Lm will give us minus m squared h cut squared. Okay, so if we take out this h cut, so we'll have h cut squared over 2, and inside we have L plus 1 minus m squared. So option B. Okay, okay, moving on, we have a particle in a Coulomb potential in 3-dimension space. In Heisenberg picture, so we are given that this quantity d by dt Lz is 0. Okay, where Lz is the z component of the angular momentum. This would imply that h comma Lz form the same eigenbasis. So is it true or is it false?
True.
True. Yeah. So this is true. So this is true because we can, so this thing will imply basically that the we know the equation of motion. So this d by dt of Lz, we can write this as iota by h cut, and then h comma Lz, right? This thing. And because Lz has no explicit time dependence, right? There is no explicit time dependence in the angular momentum operator. So this del z by del t is 0. So we will not have any second term. Sorry, I forgot here. So basically this implies that they commute with each other. And because they commute with each other, so they'll have the same eigenbasis. Therefore, this statement is true. Okay. So then let's go to the next problem. Okay. So we have an electron and it is subjected to a uniform magnetic field B, where this B is Ez, and this is the Hamiltonian, where this pi I is the momentum. Okay. So let us write our Hamiltonian first. So we are given a Hamiltonian, and for x we have, let's write this pi x squared plus pi y squared plus pz squared, where this pi I is pi minus e to the ai by e. Okay, so this quantity, this is called kinetic momenta. Okay, and it is defined like this, and this is our Hamiltonian of an electron. Then what we need to find? We need to find this commutator pi of x c by eb pi of y squared. We need to find this commutator. Okay, so let's call this quantity as k. Let's call this quantity as k, or 1 over k. So this becomes 1 over k commutator pi y and then pi x comma pi y plus pi x comma pi y and pi y. Yeah. Okay. So basically, first of all, we need to find out what is the value of this commutator pi x comma pi y. So let's do that. So pi x comma pi y. So this we can write as px minus e by c ax comma py minus e by c ay. Right? So this is then nothing but minus e by c px comma ay and plus e by c plus e by c py comma ax. So the other terms, they basically go away, right? Okay. So now we use this identity that commutator of px and any function of x is nothing but minus iota h cut del f by del x. So using this, our commutator pi x comma pi y, this becomes, so here we have p of x and ay, so this becomes, okay, minus e by c is already outside, and then this becomes minus iota h cut del ay over del x plus e by c and then minus iota h cut del ax over del y, right? So this minus minus here, this becomes plus. So it is iota e h cut by c del ay by del x minus del ax by del y. Now, what is this quantity?
This is the z component of the curl of A.
Yes. So this is the, if we take the curl of A, then this is the z component. And now what is curl of A? Curl of A is
B.
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 So then this becomes Bz or simply B, right? So because the field is applied only in the B direction. Therefore, this commutator becomes iota E h cut B by C. Okay. And if you recall, this EB by C we are calling K. So this EB by C we are calling K. So then we can simply write this as iota h cut K. Okay. So now we are ready to go back. Now we had this equation, right? We had this equation. Let me bring it down again. Yes. So now we know the value of these commutators. So here we'll just substitute iota h cut k. So this then becomes 1 over k and iota h cut k pi y plus iota h cut k pi y. Okay. So this just becomes 2 iota h cut k pi y, and this k and k will cancel out. So this becomes simply 2 iota h cut pi y. Which is option B. Okay. Is this problem clear? Okay.
Yes.
So let's move on to the last one. So okay, so here we are given some spin system, right? So a spin 3 by 2 particle. Okay, what is the spin? Spin is 3 by 2, and the Hamiltonian. So Hamiltonian H is C by H squared or H cut squared. I think H cut squared. C by H cut squared S x squared plus S y squared minus S z squared minus d by H cut S z, where C and D are constants. The energy levels for such a particle with magnetic quantum number m is equals to half is, okay. So we are given, so what are we given? We are given that the we are given that spin is, we are given that spin is 3 by 2, and we are also given that m is half. So these two things are given to us. So what should be the first step to solve this problem? So the first step should be that we see these sx and sy terms here. We should change them to s square and sz terms, right? So we know that this sx squared plus sy squared plus sz squared, this is equals to s squared. So let's take this sz square to the right hand side, and this becomes this. So now we can substitute for sx square plus sy square this quantity, and then our Hamiltonian becomes h as c by h cut squared s square minus 2 sz square, because we already had one minus sz and now we have another minus sz, so minus 2 sz squared and minus d by h cut sz. Okay, so what have we done? We have reduced our Hamiltonian to the total spin angular momentum s and the z component of the spin angular momentum sz. Okay, because we know these are the, so these will give us the basically the s and the m values, right? Okay, so what will be the eigenvalue of this s square? So we know that for this s square, okay, for s is equals to 3 by 2, s squared will give us how much? How much will I get? What is the form of this function? So it is s plus 1 h cut squared, right? And then simply put s as 3 by 2. So this is 3 by 2 and this is 5 by 2 and then h cut squared. So this will give us 15 by 4 h cut squared. Okay. Similarly, for m as 1 by 2, so this sz, this will give us, okay, this will give us what?
mh bar.
mh bar, correct. So mh bar and m is half, so h cut by 2. Now we can focus back to our Hamiltonian, right? So what will we get? So the energies that we will get E, that will be c by h bar squared. This s square is giving us 15 by 4 h cut squared, right? 15 by 4 h cut squared, and then sz is giving us h bar by 2, so sz square will give us h square by 4 and then multiplied with minus 2. Finally, we will have minus d by h cut and sz is giving us h cut by 2. So what do we have here? So this h cut squares, they will cancel out, this h cut will cancel out, this will give us c times 15 minus 2 is 13, so 13c by 4 minus d by 2. Okay, 13c by 4 and minus d by 2. Option B. Okay. Any doubts in this problem? No? Yeah, okay. So basically, whenever we have any Hamiltonian or any problem regarding either spin angular momentum or our orbital angular momentum, what what the procedure is that whenever we see these Sx and Sy, so Sx, Sy, we need to change them to Sz and the total spin. Same goes for Lx and Ly, because we know what these operators do to our eigenkets, right? So Sz does nothing, so it gives us just m h cut, and the total S gives us this Ss plus 1 h cut. And similarly, this Lz gives us m h cut, and the total L gives us Ll plus 1 h cut. Okay. Okay. Yeah. So okay, so that's it. This was all the problems that I had for today, and the time is also almost up. So, do you want to solve one more problem, or is that enough for today?
Sir, there was one more doubt that I had from one of the previous
Sure,
assignments.
sure. You can ask your doubt if you want.
It was also raised by another student in the discussion forum who felt that the question, the solution that was given was not what they thought it was. So I'll show you that question.
Yeah, you can share your screen.
So this is the question number 9.
Question number 9. Okay. So a particle is initially in the ground state of a box of length A. If the wall at x is equals to A is suddenly moved to x is equals to 3a, the wave function of the particle in the new well will be psi x is equals to 3a by 4.
I will also share this what they did.
Mm-hmm.
So I have saved up.
In a sudden move of a wall. Yeah, so this is called sudden approximation. The wave doesn't change shape, it just suddenly finds itself in a bigger box. The wave stays in its original position while the wall moves out. This proves that it must still follow our old curve, not the new wider ground state curve. Okay, so hmm. So yeah, I think this is more or less correct. Can you go back to the problem? Yeah, so the wave function.
Manam, I'm leaving.
Yeah, okay, ma'am.
Okay, bye.
Have a good night. Bye bye. Okay, so let me take a photo. Okay. Okay, so you can stop sharing. I'll share my screen and then let's try to see. Okay. So mm, can you see?
Yes.
Okay. So okay. So first of all, a particle is initially in the ground state of a box of length A. So let's write its initial wave function. Right? Psi initial. What will that be? Under root 2 by A sine pi x over A. This is the initial wave function, right?
Yes,
So
sir.
the wave, so sudden we have a sudden change, right? So from x equal to a, from x equals to a, we have a sudden change to x equals to 3a. So the wave function needs some time to relax. So immediately at just the very next instant, 0 plus, right? So our wave function remains identical. Okay, so what that means is that our psi at time 0 plus, just after the wall has shifted, so it will be under root 2 by a sine pi x over a in this region and 0 in this region. Okay, so this is how our wave function will look like. So now x equals to 3a by 4, that's what we are supposed to calculate at, right? So x equals to 3a by 4. Now this is less than a, right? So here, so what will be the wave function? So psi 3a by 4 will give us uh, under root 2 by a, and then sine of this thing, so sine of 3 pi by 4. Okay, sine of 3 pi by 4 meaning second quadrant, so 45, 135 meaning 45, so 1 by root 2. Okay, into 1 by root 2. So this root 2 cancels out and we get 1 over under root a. Is this the correct answer?
No, I marked this answer, but the correct answer was different. It was 1 by root 3a. They changed the wave function and to root of 2 by 3a.
They changed the waveform. I think that is incorrect. Yeah, so your doubt is genuine. So the wave function, hmm. So if you consider at a later time, okay, maybe that is where the confusion is coming from. So if I read the question is, a particle is initially in this ground state. If the wall is suddenly moved, the wave function of the particle in the new well will be. So maybe they are asking for some time, some later time when the wave function has relaxed and now it has stabilized to its new state, right? And but okay, I understand why this doubt is coming, because I am also getting the same problem when a problem say that a wall is suddenly moved. I think uh, it is understood that we have to find the wave function at the very next moment, right? At the very next instant. So I think the answer should be 1 by root a. So they are giving 1 by under root 3a as the correct answer, is it?
Yes.
Okay. So if we consider, okay, let's consider the new wave function. I think that is when we'll get. Okay. Hmm.
Just check with one of the TS, sir. Please.
Actually, okay. Actually, I only take these problem solving sessions, right? I I do not have any role in correcting assignments or even giving assignments or answering the questions that you raise on the portal. That is not in my hand. But
So
you can again raise the doubt on the portal if you are not satisfied.
that person, he asked the same question, but there was no response from any of them.
Okay. Okay.
It's fine, sir. I mean, losing 1 mark is not very
Yeah.
big,
Yes.
but
But the explanation that you showed me by that person, that explanation is 100% correct. So in a sudden approximation, we assume that our wave function will not change its form. It will remain as it is. Okay,
yes,
and then at some later time t, then it will change to a new function. But at that t is equals to 0 plus, right? At that next instant, it will not change its form, so it remains identical. Okay,
yes.
hopefully they will respond. Hopefully they will reply to your answer. Okay,
No,
okay. So then I'll see you next Saturday. Okay.
no. Thank you, sir.
Thank you
Bye.
for joining. Have a good night. Bye bye.